So what is Elasticsearch SQL? Magic. 35 minutes. I'll try and do half demos. And since it's called deep dive, kind of explain what's going on behind the scenes. So what is and isn't? Well, first off is work in progress, which means some things can and will change by the time we release it. But currently, it's a translator, a SQL interface to read data from Elasticsearch. Currently, it only works on one index. And it's a mix of ANSI SQL, so you get a lot of familiar constructs, but also a lot of Elasticsearch-specific functionality. Now, the idea behind it was not to make Elasticsearch look like SQL, but rather the other way around, have SQL as a way to get access to Elasticsearch. And we also focused on experience. Wanted it to be just like Elasticsearch, easy to pick up, not a lot of moving parts, just something that you can run on the cluster, give you the same 5-minute experience. Also, one thing is everything that you do still ends up being in Elasticsearch, so it's still Elasticsearch underneath. The way we're thinking of moving forward is when we release it is to make it part of XPack. This means you can use it for free. Some features are going to be commercial, but this is not going to be open source. So what isn't Elasticsearch? Well, it's not a database. Elasticsearch is not a database, so even if you put SQL on top of it, it's not going to magically make it work, which means we're not going to support everything in SQL. Things like stored procedures do not really make sense. And again, you're not going to have this external process that you have to run outside Elasticsearch. It's still Elasticsearch behind the scenes. And whatever data modeling or whatever performance issues or mappings you have in Elasticsearch, SQL is going to apply to that. As you'll see, it's quite adaptive to the runtime. So now, let's see it in action. So you saw a bit of my ASCII art here. I mean, we saw cloud and web UI, so why not go back to the basics since we're talking SQL here. So this is your typical SQL console that is connected to Elasticsearch. I can actually just type it in and see that I'm running against Elasticsearch Alpha 2 in 6.0. And I'm just going to run some commands here just to give you a kind of walkthrough of what to expect. So this is SQL, so typically you have tables. Now this map to the construct that we have in Elasticsearch, namely indexes and types. Now, until types will completely move away, they will be part of the name. So you can see here I have a bunch of Kibana indices, but also this employee database. For those familiar, this is a sample data store that is quite popular. This has been around for a while. It's just this made-up employees table with things like first name, last name, everything is generated, salary, tenure, things like that. You probably saw it in MySQL or Oracle as well. So we just took that and put it in Elasticsearch. You notice here there are some things like dep from department, but I'll come back to that later. So let's run some SQL against it. Right, you do your typical discover, which is select what's in there, and you get the columns or the values so you can see what they look like, but also that behind the scene, this query actually translates at runtime to a query DSL. This is what is called there the executable plan. So I can do selection, I can do projection, which is a fancy term from saying I just want to extract some columns, potentially do some aliasing, and also while I'm at it, I want to do some ordering here. Now, again, if you're familiar with the query DSL behind it, you can still see what's going on. There's this mixture here between the source and doc value. That's kind of an optimization. You can see the sort popping up. You can obviously do filtering. So you can say, I want to look at the employees or the first 5 employees that have been with the company for more than 30 years. Again, it's an old database, it's been around for a while, so the numbers here are big. Right, and again, at the end of the day, you still end up with the same query DSL. In fact, all the queries that I'm making here end up being executed against Elasticsearch with a query DSL. And obviously, you can end up with this. You can combine the two and have filtering. Right, I'm having this kind of made-up query where I'm looking at the tenure and the gender and the last name, and then also doing ordering. Now, whether you're a fan of SQL or not, if you look at the plan behind the scene, you see it's a bit bigger. Now, obviously, there are a lot of defaults in here that you're going to see on the screen, but nevertheless, you can give it up for SQL, right? Significantly more concise. Now, so far, I focused on the traditional SQL context and constructs, but as I said, because this is Elasticsearch, one thing is that you can plug and pull out the search functionality, the full text search functionality behind the scenes. So here, for example, I'm doing a full text search for Mary on the field first name. I can easily switch to things like multi-field, so I'm looking for both first name and last name. And you can see there I can also specify things like the analyzer or the strategy in picking up the fields quite easily. And just as well, I can do full text search of a query across all fields. I'm literally saying, got demos, thank you. Elvis and Elaine, I'm looking at them across all the fields. And just as easily, I can say, well, I'm looking for Elvis here, see whether the king is still in the building, and I can just do that. Very easily, because again, this is what Elasticsearch excels at, which is full text search. So you saw kind of the extra construct. There was a query, there was a match. I'm going to explain how that works a bit later. But also something that you see a lot with SQL are functions, where you take the data, you kind of slice it, you do a query, and then as your data comes out, you process it, right? That would be on-the-fly processing. So we support both aggregate and scalar queries. Now, this is a list that keeps growing up. So let's just start with something simple like logarithm, right? Something that everybody can relate to. So I'm just going to apply for salary. You know, it's not a big deal. But what's interesting here is that we can actually change this together. So I can apply a round function on top of an exponential on top of a logarithm and get the result. And I can also order by it. So I'm not just extracting data. I can apply custom code, my functions here, chain them together, and then do the ordering on the fly based on the result from that expression. I can, we do provide also year or date extraction, so you can have things like date of month or date of year. So looking at this database, or this table, I can say I want to find the birth date of the employees, their date from the date, but I want to filter based on the month and sorter based on the year. So you can see here kind of a scalar function being applied on the selection, on the filtering, and all the ordering. And there can be any function that we support whatsoever. And again, this translates to a query DSL that gets executed against Elasticsearch. Which leads us to a feature that we've heard a lot. People want SQL because it's easy to kind of slice and dice your data, such as grouping. So can we support groups? We can. Here I can literally say I want to group the data or fold the data, if you want, by tenure. For each group, give me the number of people that fit in that group, the minimum, average, and maximum salary, and also do a bit of ordering descendingly. And only give me the 5, basically, top groups, because I'm doing a descent ordering. And just as well, you can plug in some of the Elasticsearch statistic capabilities. This is something that we keep seeing on and on. So for example, here I can take a look at the variety, the variance of the salary. So I can look at the skewness and the kurtosis. So I can see how big the tail is and how big on the left and the right of the peak of the salary it is. And again, apply that on the group. Interestingly enough, what I'm doing here is not just doing the mean and the skew and the kurtosis, which are average or aggregate functions. I'm also applying a scalar. So I'm taking the mean and I'm rounding that up. And also at the group itself, I'm applying a year, a scalar function to extract the date, and then also do the ordering of the groups by the scalar function. All right, so you can combine things and end up with some quite powerful queries. And behind the scene is still Elasticsearch. This is one example where, as opposed to the previous one where the query DSL was quite big, here we can see actually it's quite small because Elasticsearch is an analytics engine and we just want to have the aggregation. Now, there is something else behind the scene where we kind of extract and map that to SQL but you can see kind of both ends of the coin. In some cases, the query DSL becomes larger. In some cases, actually smaller, especially when we deal with aggregations. And since we're talking about groups, we also support halving, which is here. Halving is basically filtering on groups. So not only we can group the data, so here we broke it down in two groups, first of all by gender and then by tenure. I'm calculating for the groups the average, and in this case, the variance based on popularity, or population, sorry. But then I'm also filtering. So I'm saying, okay, find me these groups, slice the data twice, so I have male and females. That's the enum that we have in this database. The tenor, right, I have some ordering here based on the tenor descending, the average and the variance, but also filter out the groups based on the result of an aggregate function. So I'm only seeing groups where the average is higher than 50K. Quite powerful if you think of the amount of stuff that you can get out of a query DSL. Now, before wrapping up this first demo, another obvious question is, okay, so what happens if we want to do joins, right? Well, Elasticsearch supports joins, but not global joins, as in, as long as your data fits a certain model, so you have parent-child, or you have things like nested documents, Elasticsearch can do those joins. So as long as your data fits in this model, you can use the same queries in Elasticsearch SQL to do that. So here what I've done is from this employees database, I took the department and ended up with a denormalized format, which is for every employee, you can see the number of departments it's been to and when it started and when it ended. Now there is a discussion here, and I'm not going to go into that, not right now, as in which way is better. There are, for one-to-many relationship, clearly you have joins, normalized joins, we have two tables, makes sense. When you have one-to-many, or many-to-many, where you have the association table in between, things become a bit clunky because you have two tables and then you have this association table in between. So there, potentially, denormalization helps. So let's take a look at the data a bit. So I'm just doing here a select. I'm just saying, okay, take a look at the department, right, which is a structure from employees, and give me just 10 things. So you can see how the data looks like, right? The department name, the department number, which is an internal thing, and then the from date and to date of that particular employee, right? Because this data is attached to something, to an employee. You don't see it here because I haven't requested it. So you can do the join, but you're not going to see the exact join keyword because this is an implicit join. In this case, it's actually an equi-join. What I'm doing is I'm joining the department table, in this case is nested, with the employee table. So literally I'm saying I want to find out the name and the department for employee number 10,020, which means I have to look it up in the, first of all, in the employee table, and then I have to look it up in the department table and then match it up. This is why it's called an equi-join, because I'm looking at a key, namely the employee number, which has to be the same in both places. And I find Mr. Warwick here. But you can also do joins the other way around, which is I want to find the employees within production department. So in this case, if you're thinking of a nested document, I'm not looking at the top level, I'm actually looking at the nested level. So I start from the department, the nested documents, and I'm looking up at the owning document that owns the data. And also doing ordering on a nested field, if you can think of it that way. Again, I don't have to specify the join keyword because the relationship is implicit. It's an implicit join. The department here is part of the from date is part of the department, which is a structure within the mapping, namely for the employee table. So I can see here the number of people that are part of production and where it was the start date. And just as well, I can go a bit crazy with it and apply some functions. So I can say, well, yeah, give me the employee number, extract the year from the date, and also do a bit of querying here. So only give me the ones that have been with the company for more than 30 years, and do a bit of ordering by start, namely when did they start. And the ordering, again, is based on a scalar function, which is applied on a nested data within a join, namely equi-join, with a criteria filter in it. So it's it's one of the things where you look at SQL, you kind of understand what is happening, but behind the scenes, there is a bit more. And again, if you're familiar with query DSL, you can notice here some things like this is a nested document here because I'm using a nested query, which is also repeated here in terms of path. So if we go back to the slides, let's see what exactly happened here. So what happens when you type something? What happens with query DS, with Elasticsearch SQL? So it's, to some degree, this is a kind of full-blown SQL engine where we have all the components in. So when we get a query, we actually parse it. We end up with a bit of a tree. We try to make sense of the tree, and we end up with a logical tree, which we analyze in order to make sense of it. Then we optimize that, and then we convert that into an actual physical plan or physical tree that ends up being the query DSL, which is then sent out to the client. So parsing is pretty straightforward. Any list of characters that you send to us, we're trying to understand what's going on there. And we end up with this unresolved tree, meaning, okay, I understand what's going on. But the interesting thing here is because we own the grammar, it means we have a lot of context of what happens where, what are these strings in one context. If there is an error, where did it occur, at what line, which makes it easy in terms of reporting errors and understanding what the user meant, including things like suggestions. Did you mean that table instead of this one? Now, once we have the tree, this is unresolved, we have no idea. Okay, I understand that the grammar is correct. We lex it, we parse it, but does it make any sense? Did you end up with a column that is not there? Do you refer to something that we don't know about? And this is what the analyzer kicks in. And this is where we, in this example here, we do this resolution, this expansion of, for example, wildcard. Here you do a filter, and we're trying to understand what that resolves to. Last, we have the optimizer, or middle, or the logical plan, we have the optimizer, which looks at the tree and tries to, well, make things faster. This is kind of the secret sauce. So we do here a bunch of things. We do things which are logical, meaning that they can apply to any other engine, but also things that are highly specific to Elasticsearch. So to give you an example, this is, right, the query that I wrote there is quite large, and if you pay a bit of attention to it, you'll see there are some things that you can remove. For example, there at the bottom would be and not false. Not false actually equals true, and true means it's always going to be valid. So this is one of the cases where the optimizer comes in, eliminates some stuff which is redundant, puts some stuff in, and in that case, it also balances the tree, which makes it easy to evaluate it. But there are also things that are highly specific to Elasticsearch. So if you look here, if I do select salary, minimum, maximum, average, those are 3 aggregations. But actually, we can map that to only one aggregation, namely stats aggregation, which already includes that. Now, Elasticsearch is fairly fast, so it wouldn't necessarily, be slow, but still, having one aggregation instead of 3 makes things faster. And we finally have the planner and the executor, which does 2 things. One is tries to track the interaction with the user and also handle things in the tabular format. So whatever results you get from Elasticsearch, whether they're just aggregations or data or a mix of 2, it kind of unrolls that to end up with a columnar format. And this is also where we handle the clients, things that expect types or have certain functions that need to be applied. And you'll see that in the second demo. Now, so far, kind of the angle was SQL. We support SQL, you get a console, we have this, we have that, but behind the scene, it's still Elasticsearch, and always is. So whatever we do, it has to fit into this, not box, but feature set, which means for better or for worse, whatever features or things that you like or don't like in Elasticsearch are going to show up in SQL. However, we try to be adaptive on things. SQL is declarative, which means you tell us what you want, and it's up to us to figure out how to do it. And we try and kind of work that out to both our advantages, meaning we try to look at the mapping, we try to guess certain things So you don't have to be too verbose about it, because actually, if your query is small, it means we can do a lot of crazy things behind the scenes because we're loose in whatever recipe we end up doing. So any search engine ends up with this concept of analyzed versus not analyzed. So to quickly recap, what's the difference between them? Well, numbers or exact things like date, if you think about it as long, are things that are exact. Whatever language, whatever context, you'll end up with the same number. But when you look at things like words, it depends. It depends on the language, on the syntax. You have a prefix, suffix, is it past tense, future tense? So this is where you start up with this idea of analyze for, where we kind of take the word, you take the root of it, you extract it whatever means possible, potentially you map it to other languages, and then when you search for it, you take the query, you get the root form of that, and then you do matching, and then return back things. So this is where the whole science aspect of it, the various algorithms to do analysis, to do search, to do scoring, so on and so forth. So if you think about it, in relational databases, everything is exact. You have tables, you have columns. There is only one value there. But now suddenly you're trying to use SQL in a world where things might be analyzed or might not be analyzed. A good example would be gender. Right? That's literally an enum that is one letter. So potentially you can map that in the exact form, or you do analysis. So how do you go about it? And this is where we try to figure things out as you give us a query, because there is no point in doing that beforehand. We don't know what query you're going to ask. If your data is fairly large, there's not much stuff for us to do. So for example, when you do the gender example, I want to do a selection based on gender M. Well, if it's exact form, which will be on your right hand side, we'll actually do a match. If not, we actually do a term query. Now again, if you're familiar with Elasticsearch, you understand that there are two types of queries. One for analyzed form, one for the not analyzed form. And we pick that up automatically based on what you ask at runtime. So if the mapping changes or if there is something new, we're going to adapt that automatically. The same thing with the data. If it's in exact form, if it's not analyzed, we get that from as dog value, which means we read the whole column, all of them in one go. If you have to specify a name and it's analyzed, we have to actually unpack the source and return it to you. Same thing with order. If it's analyzed, we can sort directly on its keyword. If it's not analyzed, we can use its actual value. But that also entails to the type of queries that we make. I mentioned full text search, and again, this is about expressness here. So I'm doing here a full text search on a field, namely first name. And because it's just one field, I can point that to a match. But if you use multiple fields, it ends up being a multi-match query. Now in SQL, the criteria, the query itself didn't change too much, but the underlying query DSL did. I mentioned we support functions both aggregate and scalar. So you have things like average, count, max, kurtosis, or things like data extraction and math. And they map to both aggregations and a mix of what is called scripting or custom processing. It depends. Again, this footnote there, it depends. So in a nutshell, when you do a group by and having, which looks something like this, right? I want some columns, apply an aggregation from where, group by, and having, which is group filtering, we do a bunch of things. We map things to a bucket aggregation to break things down to group. We potentially going to filter that with pipeline aggregation, which if you're not familiar with, it's worth taking a look. They're quite powerful. And further down, we can break a group through metrics. In some cases, we have to apply some custom processing to it, but it still works. Which brings us to joins, or as somebody famously said, joins. Now, we support both nested and parent-child. And again, as long as the data is mapped to a certain structure that Elasticsearch can use for its joins, you can actually do that. So you can see here the two types where, first off, how would a join look like? Well, again, just by referring to the name because it's implied. Why is it implied? Because it's part of the mapping. So there's no point in specifying the join keyword. We already know when you specify the field because, hey, it's part of the mapping. Again, the idea here is to make the query small and use the environment, use the context rather than making you specify things that might be wrong and then end up with an ambiguity. So in this case, in the first case, I'm literally looking at and doing filtering based on the equality of it. I'm looking at the key employee number, which has to be the same within the department and within the employee. This is the equijoin. Or I can actually flip things around and not look at the employee, which is, you can think about it as a root or the owning document, but actually as a nested document. If using nested documents, or if using parent-child, you look at the child and then figure out the parent from within, from underneath. Which we're doing here, we're doing filtering based on the department name and then figuring out the owning document, namely the employee. One thing that I like to touch on is what do we do on the client side? And what do I mean by clients? So you saw the CLI, the command line, something portable. Currently, you saw this prototype, which is, gives you it's portable. It's has this text functionality. It's mainly meant for quick prototyping and admin type of thing. The idea for it is to be specific, just like typically you would do with the command line for your database. We also support REST. So if you use Kibana, you can actually get access to it. So you can end up with JSON, and you can play around with it. There is a subtlety here, namely in the command line, you end up with SQL because it's a SQL command line. When you're doing REST, you're actually using JSON. So in terms of how the data is represented and the types, things change a bit. So you still have this idea of a tabular format there. You have things like type and the first name and last name, but you'll notice that the types are slightly different because, again, this is JSON. So the way you represent the data in JSON is slightly different than the way you would represent that directly in SQL. And last but not least, we have a JDBC driver. And this one, well, it doesn't sound like much, but actually it's quite powerful because you can do a bunch of things with it. First of all, it's a full-blown 4.2 type 4 driver if you're into that type of thing. Supports both the Java SQL and Java X SQL APIs, including stuff like logging, which is nice to have, but not a lot of drivers support. And it's embedding safe, which means it has no dependency whatsoever. So whatever libraries you potentially use in your application, if you want to use a JDBC driver, you can just plug it in. It doesn't depend on Elasticsearch, Commons logging, or whatnot. And since you have a JDBC driver, actually you can plug in whatever tools you have that use JDBC and point them back to Elasticsearch. So let's see how that looks like. So this is Kibana, just to quickly show. Right, this is my node that runs on localhost. I have SQL in this case. I just extracted from XPack, and you can just run the query and get the results back and see how they look like. Number of rows. This is kind of the schema at the top, so you know what to expect, and then the actual rows and their values. Speaking about SQL and JDBC, I have here two tools. One is, well, both of them are free. One has also some paid for commercial functionality. So I have here Squirrel SQL client. I just declared Elasticsearch here. I just plugged it in. I created the alias, and now I can just kind of look around, and you can see the bunch of properties that it has. We actually implemented the whole metadata, which is useful because it means whatever type of escaping or quoting your client might use is just going to work because it has all the information, right? So you can run the queries. What do you expect? Or you can also do things like, I'm using here just for the sake of the argument, a different tool named DB Visualizer to connect to it, see the tables, right? See what they contain, the type of columns, example of the date, and also I can run your query. So because we, as I said, support grouping, you can do things like I want to get the minimum, average, maximum from tenure, group by tenure, and then apply a having query on top of it. So I can just execute it, the whole query, not just tenure. You probably saw in the error message, line X, column 14. This is real. Not making this up. And then you can just take the data and basically fit it in. Now, the eye candy is based on this tool, right, DB Visualizer. But the whole querying and connection to Elasticsearch, that's through the JDBC driver. You just plug that in. So you can just take a look here at the driver manager, and you can see, I have my JDBC driver. This is what it looks like. Plug that in and can point the client to it. So that's it for me. If we can go back to the slides. If you have any questions, there's still 4 minutes to go and happy hour waiting for you. So thank you so much.
Thank you, Costa.